Okay. Last time this was too loud. Testing, testing, testing. Okay. Okay, so here we go. Welcome to those of you that are online. There's a delay, so they won't actually hear it until a couple of seconds, but we can't see or hear them anyways. So today we're going to talk about 3D frames and machines questions. I guess these are kind of made-up problems. They're not real things, but and these problems are a bit complicated. So let's start on this first one. So this one you have kind of like this bent pipe, which is ACD, and it fits kind of loosely into this like holder ED, which is on a smooth rod that's kind of like brass or colored, copper colored, right? So this one, you could kind of look at it, you could do it a couple different ways. So you could look at it and try to, like, in your head, count reactions and you're looking for shortcuts, right? Now, you know that you have two bodies. Well, you can think of it as being two bodies. So the rod is completely fixed. So that one you don't consider. So the two bodies you're going to look at are this ED and DCA. So you know you're going to have 12 possible equations that you could use, right? So you have sum of forces and sum of moments, 3 equations each for two bodies. So it's 3 times 2, 6, and times 2 again because you have two bodies, 12, okay? All right, so the first thing, what would you do looking at this?
Started with a three-body diagram of either ED or ACD.
There you go. All right. So let's start with ACD. But the strategy that I would take is draw a free body diagram, see if look to see if you can find any things you can solve for right away. So you might jump to sum of forces, you might jump to sum of moments. Sum of moments is really going to be your friend here, right? And then if you can't find anything, try the other body, right? Or different combinations. So let's do ACD. Now the other thing is for your homework, either if you have a tablet, great, you can do what I'm doing. If you don't have a tablet, you might want to print the homework out and trace it, or just do this. These are going to get really complicated, right? And so you want to draw them as neatly as you possibly can. So I'm going to draw it on top of the body. That's breaking the rules, but I'm going to move it later, right? Because I have a tablet. So you might want to trace or do something else, right? Well, this doesn't exist. Okay. So first, I know I have a cable. This should be like old hat for you right now. I'm going to call this FAB. Okay. And then I have my force. We're doing the easy stuff first. So this is 2.5 kilonewtons. It's down in minus K direction. I'm not going to write that. At C, what is that? It's a roller, and it's going to make a force in the x direction. So I'm going to do Cx. And then what about at D?
Cross bearing. Because it's got a, right? X, Y. Well, for member ED.
So that roller is on member ED, but we're not drawing member ED. So this is like a pipe going into a smooth hole, right? And now that I think about this, it wasn't quite clear is that pipe bottomed out in that hole or is it not, right? So turns out it's not going to matter. So what you can do is you can kind of draw your free body diagram, and you can kind of look to see if you have any, if you need that force or not, or if you don't. In this case, we won't need it, but we'll add it because we'll see it won't matter, okay? So what kind of reactions am I going to get at D then?
Force in X, Y, and Z then.
Yeah, so I'm going to get a force in X, Y, and Z. So the first thing I'm going to do, just to kind of make so my drawing is pretty good, is I'm going to draw a coordinate system, but I'm going to not draw the coordinate system that I'm given. So I'm going to draw a Z direction. I'm going to draw an x direction, and I'm going to draw a y direction. So all I've really done is just shifted the coordinate system from where it is, because otherwise it's not even on the body that I'm drawing. So this is more convenient for me. And what did you just say? I'm going to have a z force. So I'm going to have a dz. Now, we have to be super careful here, because I'm calling this dz, but when I do body ed, I'm going to have a dz from the roller. Those are different. Those are not the same, right? One is the force the roller puts on the member ED, and the other is the force that the member ED puts on member DCA, right? One of those is going to be a Newton pair that'll have equal and opposite. The other is just coming from a reaction. So to differentiate that, I'm going to call this D prime. So all the forces between ED and DCA are going to have primes on them. You don't have to do it that way, but you do have to somehow say that you have to give different names to your different forces, so you don't get confused, right? What about next at D?
Another force in the x.
Yeah, another force in the x, good. So we'll call this dx. And now, y is the question mark, right? So like, do we have a force in y or not? Let's do dy. Oh, these should be primes, right? And let's talk about that really quick. So I did a dy. Do I have any other forces on the system acting on y? No. So dy is going to be 0, right? So it doesn't really hurt to have it there. It doesn't really help to have it there. But because we don't know, we'll say maybe there could be a force. Maybe that thing is actually bottomed out in that sleeve. And if it can't move, then there's going to be a force there. But we're going to get 0 anyway, so it doesn't really matter. Okay? Okay, are we done? No, because we couldn't, when you have like that thing in the sleeve, you couldn't twist it, right? So can you twist it about the y-axis?
Yes.
Yes, because it's the key wording there is that it is smooth circular hole, right? So that means that we can twist it that way. So there can be no moment along the y direction, or the dy. Can we rotate it about x? No. So now I'm going to call it mdx. I should call it md prime x, but that's going to get too complicated. So I'm just going to call it mdx. There's no moments happening at point D, so you shouldn't get confused. And what about z?
A moment generated.
Yeah, same thing. You can't rotate about that. So md, mdz. Switch my eraser so there, that's what I want. Okay, so I think we're pretty close, right? And the only other thing I want to do is I don't want to like write a direction for this because it's already getting kind of noisy. So I'm just going to show that it goes from point A to B. So this is going to be A, this is point C, and this is point D. And things will get a lot cleaner when I move this. So I'm just going to drag it away. And so there's my free body diagram, right? And so this is my FBD of ACD. And how many unknowns do I have?
7.
Yeah, so I have 5 unknowns. Wait, is that right? Yeah, I have 5 unknowns at D. I have the unknown at C, and I have the unknown of the cable. So that's 7 unknowns. So that tells us we can't, what does that tell us?
Can't solve it currently.
We can't solve what?
The body. Or not the
So it tells us we can't solve for all 7 unknowns,
Yeah.
right? We can solve for some of them. Well, not always, but in this case we can, right? So now here's the tricky question. Which equation, can you see an equation that's going to give you just one unknown? You can do this systematically, right? So you look at x, you have the x component of FAB, you have CX, okay, we're done, right? You also have DX, right? You look at y, all right, that one you can do by itself, but it's kind of trivial.
Some of your x, I mean your z's, because you only have
Your,
O and you're only
your forces in z, not quite, be careful, remember, we don't know dz, or d prime z, and we don't know FAB has a z component, and we don't, well, that's it, that's 2. So that's 2 unknowns, yeah.
In terms of the unknowns, like, technically we have 7, but don't we already know dy has to be 0?
Okay, but if you're going to say that, now one of your equations goes away.
If we take moment about the x, and the cx is acting in the same direction.
Wait, say that again. We take the moment about which axis?
Moment about the x-axis.
Okay, if we take the moment about the x-axis, FBD causes a moment about the x-axis, and MDX is a moment about the x-axis. So that's two unknowns. But you're getting on the right track. So I'll give you a hint. You're going to want to take the moments about the axis that doesn't have a moment reaction, the y, right? So if I take moments about y, nothing at D does anything because all those forces are applied on the y-axis, the new y, or the y-axis that we drew here. Cx is on the y-axis, right? So this is going to relate the 2.5 kilonewton force to the cable. So we get the cable straight off, right? So let's write that equation. By the way, I had the answer for this and I erased it. So, all right, so sum of moments in y is equal to 0. So now we got to do something, right? I'm not going to be able to write this equation because I don't know what the y component of FAB is. So let's just do that. So FAB. Oh, and I told myself I was going to call it T. Oh, well. So force FAB is going to be its magnitude multiplied by its direction, RAB. And then do not forget to normalize RAB. So that's going to be FAB multiplied by, now we look, so from A to B, the x dimension is 0.3 and 0.3, so that's 0.6. But it's in the negative direction, right? Because we're going from A to B. So that's going to be minus 0.6 or minus 3/5 I. And then the y is 0 because it doesn't, they're both at the same y coordinate. They're both at y is equal to 0.9, both points A and B. And the z is 0.8, so that is plus 4/5. And one thing I do not like about this problem is if you forget to normalize it, you're fine. But, right, 3/5 squared plus 4/5 squared is equal to 1. So it's already a unit vector. So I'm writing divided by 1 here just so like I don't want you to think that it's just the radius times the force. Okay? So now we can continue on. So sum of moments in y is going to be equal to, okay, so now we need some distances here. So we know that the, let's see, we'll do this in blue. We know that the distance from the y-axis of the 2.5 kilonewton force is 0.3 meters, and the distance of A is 0.6 meters. Just do 0.6, right? And so what we're going to get is the 2.5 kilonewton force positive or negative moment about the y-axis? Positive, right? So we're going to have 0.3 times 2.5. FAB will make a negative, right? It'll be the negative component, and which one do I want? The x, the x component or the y component of FAB?
The z component.
I'm sorry. Yeah, you're right. The z component. So good. That'll make a negative moment about the y-axis. So we'll get negative 0.6 as our distance, which is the distance in x. The distance in x should be multiplied by a force in z in order to get a moment about y. And so the z component was what, 4/5. 4/5 of FAB. Hopefully somebody is computing this for me.
Yeah, I got 1.562.
That's right, yeah. So FAB is equal to 1.5625 kilonewtons, and you could round it, but that's exact.
I do have a question with the three-body diagram.
Yeah.
On the original schematic, it shows a negative 2.5 K.
Yeah.
So wouldn't that mean that arrow is then pointing upward if we're stating it's positive?
No, they're not trying to trick you like that. They're only giving it to this so that you can see that force is actually pointing like downwards,
Yeah.
right? And not like,
I took it as a variable.
Yeah, no.
Direction.
yeah, no. I mean, if this were an exam problem and you did that, we'd be annoyed, but we'd be like, okay, we won't give it to you that way. No, what they should have done is they should have said, now if they wrote like P, and then they said, and they wrote it like P with like a not hold, It means P going down and its magnitude is P. And then they wrote in the problem state that P is equal to minus 2.5 K, bold. Then the drawing is showing you the direction and the magnitude, and the text is showing you the vector. And they'd be consistent with each other. But like, no, I mean, if you're confused, ask. That's not something like I'm particularly worried about. We're not going to try to trick you like that. We have enough things to worry about. Okay, so that gave us FAB. Is there any other low-hanging fruit that we can get out of this?
And dy,
Okay, dy was super low-hanging fruit, so we'll take what we can get. So sum of forces in y is equal to 0 is equal to dy prime.
Get forces across the z.
Yeah, so can we get forces in z? Yes, we can, right? So if we do sum of forces in z is equal to 0 is equal to, what is it, 4/5 again? FAB. Plus or minus 2.5 kilonewtons plus d prime z. Am I getting that right? I think so. Okay. What do we get? It's positive, I think. Yeah, it's definitely going to be positive.
I got 4.53.
I don't think that's right. So I kind of remember this. So 1.5625 times 4/5, I believe, is 1.25.
Oh, wait,
Right? So that it's 1.25 plus 1.25 minus 2.5 is 0. So I think dz is also 1.25 kilonewtons.
yeah.
Okay, cool. All right. Now, if you're at this point in the problem, we made one key mistake. Like, what are we doing? What are we trying to solve? So let's look at the problem statement really quick. So it's saying determine the x, y, z components of the reaction at E, which we're not even talking about yet because it's not even the body we're talking about, and the tension in cable AB. So all of this that we're doing is solving for these d prime forces wasn't even asked for. Turns out we're going to need them, but just this might be a point where we actually want to jump to the free body diagram of the other part. So these problems, you're going to jump around a little bit, right? Because you're just looking for, this is like Sudoku, that's what I said last week. You're looking for easy things you can solve. And once you solve something, it might make other things easier. So it literally is like Sudoku. Okay. All right, so I'm going to zoom in and trace this guy. You don't have to like draw them perfectly. You just need the outline of the body. It's nice if it sort of halfway resembles the thing that it's supposed to be, though. All right, so there's my body. Now, I'm going to have, like we said before, I'm going to have a dy, but I also now have to satisfy Newton's third law. And every reaction I had at D, I have to add an equal and opposite reaction at D for the other body, including moments. Moments are also equal and opposite. Okay? So the way to do that is I just copy, right? So I'm going to do a d prime y acting in the downward y direction. Yes, which this was also z. Thank you. I'm going to have a dy, this is 0, but d prime y. And I need an x, so I can do that one maybe going this way, d prime x. And then I'm going to have a m dz acting in the downward z direction. I'm going to have an m dx acting in the negative x direction. I will not have an m dy because I didn't have it otherwise. So that takes care, I think, right, of all my reaction forces there. And then what about at E?
Smooth collar.
Smooth collar, yes. So let's do the forces first. Forces are easy, right? So I have an EX, and EY. Okay. Do I have an EZ? No, because it's smooth. Could I twist this thing about the x-axis? No. So I'm going to have an MEX Could I twist it about the y-axis? No. And M, E, Y. Can I twist it about the z-axis? Yes. So I don't have a moment. All right, so you have to ask these questions to yourself. All right, now we'll just think as to where do I want to put my coordinate system. We can just, here we can might as well just stick with the original one. Okay, I think the only thing I should be missing at this point are dimensions, right? Which we'll add them as needed.
One.
What's that?
You only really need one.
One dimension?
Isn't it just 0.5 meters?
Yeah.
Yeah, you're probably right, but I still am lazy. Uh-oh. How much, does anyone actually buy their book?
I pirated it.
No, that's not what I asked.
You don't supposed to say that out loud.
Yeah, this is like recorded too. Does anyone actually buy their book? You did? Full price? Do you mind, what does it cost? Like more than $100, right? Yeah. One of these days I want to try to I don't know if we have the ability or the time to do it, but write our own book and then ask you guys to buy tablets instead. That sounds, what's it?
Expensive for that.
You can get it like a cheap iPad for like $200, which isn't that much more than a book. So, anyways, you can't pirate a tablet.
Definitely. Oh.
All right. So here it is. All right, now going back. So this looks daunting, right? So first, let's count how many new unknowns do we have. I don't care about how many we have total, right? All right, so we have MEX1, EX2, MEX3, EY4. All these other things are the same, and 5, right? So 5 new unknowns. Wait, what? No, 5 new, right? 1. So MEX, EX, MEOI, EY, that's 4. And then just DZ. Everything else is like coming from the other body, right? So if you look, 5 unknowns plus 7 unknowns is 12. We should have a solvable system. A little late to know that now, but anyways, that is. Okay, so what can we do here?
Well, you know that EY has to be 0.
What's that?
You know that EY has to be 0 because D prime on 0.
Okay, so we could do sum of forces in y is equal to EY minus D prime y, but that was equal to 0, so EY is equal to 0. This was actually something we wanted to know, right? Can we do sum of forces in x?
Yes.
Although I don't think we can solve that yet.
Well, we don't have D prime.
Yeah, we don't have that yet, but we can do it. Well, let's back off a step, because we know we can't do it, right? So,
Can we first solve the experiment on the free body diagram and then like go back to the
wait, say that again? You could, but there's an easier way. So let's look, remember, like, how did we get the first easy thing on the other problem? We did sum of moments about y, right? What happens if we do sum of moments? So we did sum of moments about y last time because that body was kind of free to spin in y. There were no moments constraints, right? Now this one, if we do sum of moments in y, the body can't spin in y. So that's not a free. But there is one axis on which the body is not constrained by the support at E. And that is the z-axis, right? So this is point E. This is point D. Kind of obvious from all the forces, but anyways. Okay, so let's just look at that. What happens if we do sum of moments about the z-axis? So what do we get? So nothing happens at E that's important, right?
So what are the D prime X?
Oh wait, there's MDZ though. Maybe we could have gotten that. MDZ is coming from, right, because we still have MDZ.
Oh, yeah.
And if I look at this, MDZ, so this is where we're going to go back and forth some, right? Because we're like, you could just go nuts now and just write out all 12 equations and plug it into your calculator and write out a 12 by 12, but don't do that, right? Like, you probably won't do that without making a mistake somewhere. So you're looking for easy equations, right?
Yeah, couldn't you do the normal force at D?
Couldn't you do the normal force at
So
D?
Because we
DZ
found D
equals
prime
D
Z.
prime Z,
Yeah.
but we don't know DZ yet. Or no, we
We
do know.
find it that way.
Yeah, DZ is just
D prime Z.
1.2.
So DZ we know. We can do sum of forces in Z, but that's not super interesting. That's just going to give us that DZ is equal to D prime Z, right?
Yeah.
Can help us for other moments.
Yeah, then we can do the moment and the x-axis.
Actually, let's think about that. What are the moments about the x-axis? Let's do that one first. Well, let's do what you just said. So let's not do too much in our head. So sum of forces in Z is equal to 0, is equal to dz minus d prime z, and d prime z therefore, or no, we knew that one. dz is equal to d prime z, which is equal to 1.25 kilonewtons. That's not something that was asked for. But now, like you just said, we can do sum of moments about x is equal to 0, and that is going to be what? So that's going to be m ex.
Well, wouldn't that just be 0?
Yeah, right? And so we're going to get, not that the length matters here, you said this was 0.5? Right? So I'm going to get plus 0.5, and it's the same distance for both forces. Like this is a little bit. So dz will be plus minus d prime z, but because z and d prime z are equal to each other, this tells us that m ex is equal to 0. Probably should put some units in there. So that is kilonewton. It's whatever units of a moment you want, but do that, right? So how are we doing? So we needed to get,
We still need EX and Y.
we need ex, ey,
Well,
we have ey.
MY and EX.
Yeah, all right. All right, so we got to tackle maybe the x's next. So now we just have to look, right? What else can we do? So we don't know, what's that?
We could find d prime x by sum of moments in the z-axis, the free body diagram ED.
Wait, which one?
Free body diagram of ED.
Free body diagram of ED, and what you want to do sum of
Take a
what?
moment at z-axis.
So if we do the z-axis, we will have, well, we don't know MDZ yet though, right?
Oh, yeah, no.
Let's see here. Can we do anything about, so we don't know what dx,
At this point, I think you'd have to take the sum of moments because with DX, if you're trying to find it for force, you would need to then solve for CX and D prime X.
yeah, no, there's got to be a, let's see. So we've done sum of forces in y on the first free body diagram. Sum of forces in x, we have two unknowns.
I mean, if you do,
We can do sum of forces in z, can't we?
yeah, and then you can find CX and then use the force.
Yeah. So let's do sum of forces in z here is equal to 0. So this is going to be, oh wait, we just did it. Never mind. I'm sorry. All right, let's just write out sum of forces in x because we haven't done it yet. Right, so this is minus 3/5 FAB, which we know, right? Plus CX plus DX prime. Now we can't do anything, there's two unknowns there. But, okay, here's what we,
Yeah.
Because then you can find CX.
Yep.
And then we know what FAB is.
So sum of moments in Z is equal to 0. But I'm not sure about that because we're going to have MdZ, which we don't know, right? Then we have nothing else coming at D. Then we'll have CX. So I need to know that distance. Well, let's just start writing stuff out. So this distance is 0.4, right? Yeah, I think it might not be too bad. So we'll have, so CX is going to make what kind of moment about Z? Yeah, minus 0.4 CX. And actually, this may not be too bad. Let's see. And then FAB is going to be the X component of FAB, right? So it's going to be plus 0.6 times 0.4 times FAB. This one may not be super helpful to us because MdZ is not going to come out easily from this, I don't think.
Yeah, but then won't we do another sum of moments in the Z direction for the other free-body diagram, and then just do the system equation with 2 unknowns?
Yeah, but I thought there was a way around that. Let's see, so we've done some moments about Y, which we've already used. I'm just going to put like a little check mark. It means we can't really get anything useful out of this. So this is open, and we still have some moments about.
X, but I'm not sure.
Let's just write it out because we need all 6 equations in the end, right? So sum of moments about X is equal to M dx. This is actually we'll get this, right? We'll get MDX, right? And so this is going to be minus 0.4 times 2.5 kilonewtons, right? And then FBX is going to make a positive moment. So it's going to be 0.4, and I'm being a little inconsistent here. So it's going to be the Y component, right? And that is 4/5 of FAB. All right, so that we can solve, right? Anyone want to do the honors? So 0.4 times 2.5 is 1.
That's what we got at 0.5.
Yeah. 0.5 kilonewton meters, which also we don't need to know. But now, see, so, wait a minute. We made some mistake, haven't we? I just said MDX was equal to 0, didn't I?
MDX, I mean, you just said it's 0.5.
For the other one.
Oh, we forgot to add.
D through C.
Sum of moments about the x-axis is MEX
Plus or minus MDX.
Oh. Or MDX, right?
Yeah.
Well, that didn't really change anything. So MEX is equal to 0.5 kilonewton meters. Well, that's not good news for us, right? Because so now this is done. So we still have to use these two. This is done. This is done. All right, let's just write out the rest. I must be missing something here. Sum of forces in X is equal to 0. And so here I have EX
minus d prime x.
minus D prime X, which we don't know, right?
I believe so.
No, we don't know. Although we could solve for it in terms of CX. And what else do we have here? That's it.
Yeah.
Okay. And then we don't have the other moment equations here. So sum of moments about Z is equal to 0. And this one is going to give me, sum of moments about Z is going to give me minus M dz. And then just 0.5 times dx, right? Times d prime x. And nothing else, right?
That would just be 0, wouldn't it?
Hmm?
On ED, because there's a moment in the Y, but it's only one thing, and I don't think there are any other forces that cover a moment about E in the Y direction.
Which will be dx, yeah, d prime x. Or now that answer y. Yeah.
You're asking if I take sum of moments about y? Well, we did that, didn't we? We didn't do that.
0.
Yeah, we haven't written.
Oh,
that.
MEY will be equal to 0, right?
Yes.
Yeah. Okay, so that one's pretty straightforward. Okay, yeah, so that's another one. So now basically we just need EX, I think.
Yeah.
Okay, and that's going to come out of this term, right? So we can write dx so we can write d prime x in terms of EX MdZ is showing up here. Yeah, it's going to come out of this, I guess. Right? So if this is equation 1, and this is equation 2, and this is equation 3, we've solved for everything else. Like this equation is done, 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 done. Done. So 2 equations. Wait, and this something's not right here. So what don't we know? So we don't know.
Well, that gives us 3 unknowns, 3 equations.
How? But we also don't know this one. Sum of forces in x is equal to 0. So I think we have 4 equations. So our unknowns at this point are EX, D prime X, CX, MDZ. Right?
And then there's 4 equations.
That gives us 4 equations.
I would just put in the matrix.
Yeah, I think that might be the best. You might not, I mean, there's like, equation number 4 is you can just do a substitution everywhere you have a d prime x, it's just EX. So that's really like 3 equations of 3 unknowns. Actually, you don't have EX anywhere else, so you can just ignore that equation,
Yeah.
right? And then the MdZ shows up in just 2 of the equations. So if I substitute MdZ for 0.5d prime x, or vice versa, if I substitute everywhere I have an MdZ, I just replace it with 0.5d prime x. That's probably better because, or no, that's what I just said. I want to get rid of the d prime x's because I don't care about that. That's not something that's asked for. So I can put an MdZ where I have a d prime x. So I could probably pretty quickly make it 2 equations and 2 unknowns. Okay, we good there? We good? Still a homework problem, so I'm not going to completely finish it. All right, hopefully we didn't make any terrible mistakes, but that is Yeah, this is a big one, right? So this is like, take space when you do this. And don't get, when you do it on a tablet, like I can do this. When you do it on a sheet of paper, you cannot. So like give yourself a good chunk of you could even use a whole page to do your free body diagrams and then do your work on the next one. But what's really critical when you do your homework problems is make sure we know which equations correspond to which free body diagrams, because otherwise you'll never follow it, right? So in this case, like I kind of put them next to the free body diagrams. Yeah.
With these problems with so many opportunities to make mistakes, is it going to be graded in such a way that if you had made a mistake on one thing, chances are it's going to affect everything else? Will it kind of like do domino effects? Because I know some of the homeworks in the past have done that.
Yeah. So you mean like everything will be wrong?
Yeah.
Yes.
And so it's going to be graded.
Well, okay. So here's the thing. Like you might have already realized this. We can't give you this problem on an exam. This took 40 minutes, right? Right. So we cannot give you this problem on an exam. So we can only give you a slice of this problem on an exam, right? So
It's a one-question problem.
what do you mean a one question? Yeah, that's a high risk. You don't want that, right? That's like all or nothing type of exam, right? No. So think of the concepts that are really important. Like if you were solving this problem, would you be able to draw these two free body diagrams, right? That's fair game, I think. And that's not crazy long, right? So you still have to recognize. Now, if you did the exam, right, we had some questions. Like, should we have added d prime y in there or not?
That's what I was telling him right now, that I did solve it and I'm getting the same answers, only that I never used the prime or anything. Because I wasn't really sure if there was like
Oh.
a force right there, so I just like ignored them. Well, not ignored them, but I just didn't know there was like a D prime and everything, and I still got like the same.
That might have worked out because at E, there's no force coming in the z direction. And so in the final answers, it shouldn't have mattered. But where it would show up is the force between member ACD and member ED in the z component might be different from each other. Did we even solve for that yet? I don't know. Z, we did solve for it. So d prime z is 1.25. Is that what you had?
Well, I didn't.
1.25. No, you did. You found the same one. Yeah.
Well, this equation wouldn't have made, so the sum of forces in z wouldn't have made any difference on body ACD, right? And then when you go here, what do we have? So we have a downwards force and an upwards force. So then what did your free body equation of ED look like?
So I did two force body diagrams. The first one was the little ACD, and then my other one was like the whole thing.
Oh, so
Yeah, she did a rigid body.
yeah. So I think you may not have even had the force that we're talking about then, or it wouldn't have mattered. Yeah, so that's the flip of it. There are certain, I don't want to, mistakes. It is a little bit of a mistake, but that's not too bad. There are certain things that you can do where you'll change like how the internal forces are transmitted to each other, but you haven't actually changed the problem. So that seems like your case. Yeah, but in reality, like if member D, or not, if the roller at D is putting a force on member ED, which is what the picture kind of shows, right? Then that force from the reaction does not get exerted directly on ACD, right? There is a separate internal force between those two. So you should have three forces. Well, two forces. You should have dy and then this like d prime or whatever you want to call it, right? But in your case, it looks like you got away with it. So, yeah. Okay. Let's do the next one. The next one is, I think, actually a little harder. But I think are there only two 3D problems, right?
Yeah.
Okay. All right. So yeah, we're walking you through both of these. Okay. I don't know how far we'll get with this. So this one, same deal. One thing I want to point out is member C is like all that funky stuff happening at C don't draw two bearings and all, like, C is a connection of itself, right? So we only have to ask questions is what can or cannot happen at C. We'll get to that when we get to it. All right, let's do AB first. And I'm not necessarily picking the smartest way of doing it. I'm just acting as if I was taking this in my own quiz or something like this, and you gotta do something. You can't just sit there for hours. All right. So what is A? A is a ball and socket joint. What does that mean? Three forces. Yeah. I want to draw my coordinate system first. So here's my Z. Here's my Y, and we're going to do exactly the same thing. Here's my X. So three forces, real simple. So I have an AZ, and I don't care that I'm going to overwrite stuff because I'm going to move it off anyways, an AY, and an AX, okay? And I have an applied moment acting 800 Newton meters. And what about B? Smooth collar. So what forces is it going to exert? X and Y and no Z. Yep. So X, Y, moments. In fact, we just saw this, right? It's the same thing. So we have a M, B, Y, and a BY, and a BX, and an MBX. And anything else? We have some dimensions that I'm not going to do yet. That's it. Oh, come on. All right, good enough. All right, any low-hanging fruit here? Actually, I think I might have done something. A moment about X. Are you sure? There's an MBX.
Yeah, MBX is equal to 800.
What about AZ?
It's going through the axis.
Oh, that x-axis. Yeah, I see. I was not even thinking of moving the x-axis. All right, so sum of moments about x-axis is equal to 0 is equal to, yeah, nothing at A is going to do anything, 800 Newton meters. BX obviously can't, BY can't, there's no Z component, plus MBX, so MBX is equal to minus 800 Newton meters. Okay, good. Anything else we can do? I really want to write out moments about Z, right? But I'm not sure I want to do it. So if I write moments about Z, it's going to give me a relationship between BX and BY, right? So we could do that. But let's put some dimensions in. So my X distance is 3 meters and my Y distance is 2 meters. Okay? So moments about the Z-axis are going to give me that, what, 2BY minus,
Oh, wait, no, sorry. X. Yeah,
minus 3BX is equal to, I think I screwed that up. Yeah, so it's 3BY and 2BX is equal to 0. Okay, so that gives me a relationship between BX and BY. Let's see here. Sum of forces is kind of, we could do sum of forces in Z, right? It's a very low-hanging fruit. AZ, that's all we have to write. All right, I think we're good. I want to get to the other free body diagram anyways. So I'm going to zoom in and take my time, draw something. Now, I'm not going to draw any of this fancy stuff here because I'm just going to consider that as a constraint. Okay? So I've got a force of 250 newtons. I'm going to draw this really carefully. These are, what are these called? You remember? Pretty close. Coordinate direction angles. But I think, yeah. So it's 45 degrees to the x-axis, I'm sorry, 45 degrees to y-axis and 60 degrees to the z and x-axes. And the kind of hint there is remember like cos 60 plus cos 60 plus cos 45 has to be equal to 1, which I promise you it is. Okay, so that's the load. Now we have to take all the loads that we had at B and just flip them, right? So we'll have an BX and an MBX and a BY and a MBY. And what about C?
Smooth pin. I think it's
Smooth
I think
pin.
it's called-
Yeah. So the easiest way to do this is to say, well, which way can it move?
No direction.
Well,
Translation.
How does it allow it to move? What are the,
Moment about
it can rotate about X. So it has to have everything else, right? So it has a CZ and a CX and a CY and a MCY, not an MCX, because otherwise it wouldn't be a pin, and a MCZ. Okay. So let's count our unknowns again. So at C, we have 5. The easy way to know that is there's one way it can move, so there must be 5 ways that it can't, right? So we have 5 unknowns there. I won't count B because it's on the other free body diagram. So the other free body diagram has 4 unknowns at B and 3 unknowns at A. So that's 7. 7 plus 5, we're back to 12. So we have a solvable problem. Hooray. Okay. Gosh, this is messy. Where do I want to put my coordinate system? I kind of already drew something, but I don't know if I really want that to be...
Yeah.
Yeah, sure, why not? Doesn't really matter. Sometimes it might be like a little more convenient. Actually, I don't think I want it there. Because if I take moments about...
Or bring it all the way down.
Yeah. So I'm going to leave it there. So I'm leaving it like those guidelines. Those are still lines that are parallel to X, Y, and Z. They're helpful for the directions of the force, but I'm not going to put my origin there. And you don't have to put your coordinate system, like, you could have left it up there, and, you want to write your moments about C, then you just write your moments about C. But I think for visualization, it's nice to see the coordinate axes when you say I'm going to take my moments about C. So that's why I like to draw them this way. The thing that I've noticed, like on exams and quizzes and things like this, is, and I understand you're freehand drawing these things, but it's really hard, like for me, to look at your exam and see if your moment equations are right, if your lines aren't in the directions they should be. And so if it's really hard for me, I imagine it's also really hard for you. So try your best to draw these well. Homework, you can use a ruler and all that jazz, but exam, I understand. If we give you something on an exam, we'll probably try to, like, I'm thinking of ways I can give you something without giving it to you, right? Give you something so that you don't have to draw really well, but you still have to know what you need to know. Okay, wow, what a mess. What do we want to do?
Lowest thing would probably be the moment in CZ.
The moment in CZ. I think forces in Z would be a low one too, but let's do what you say. So the moments about Z. We can just say Z, because that's what we call the axis now, right? So none of the forces, well, this is really low, you're right. It's just MCZ, right? Okay. Hey, I think that was one of the things we wanted to know, so cool, that's good. I don't know, what is the problem asking for? It's asking for, yeah, the reactions at A and C, so good, okay. And another kind of low-hanging fruit, I think, is the the forces, right, in Z. So you have CZ, which is going to be negative, plus, what do I do?
Cosine of, what's that, V? Cosine
60 times 250. So you can calculate that. Cos 60 is, I believe, a half. So CZ should be equal to minus 125. Okay, so that's another one. X isn't going to be super easy. Y isn't going to be super easy. Moments aren't going to give, you know, so like one way to think of this is if I add a moment equation, then if I add a new equation and it adds an unknown I wasn't using before, it's not helping me. I mean, unless I look at all of them, right? So I think that's the easy ones there. Let's go back to this one. So we did moments in X, moments in Z. Do we want to do moments in Y? Probably. All right, I'm just going to write it out for completeness. I don't think it adds another unknown. So it's not super good. So MBY. And what else makes a moment about
I'll go through the line of action.
AZ, doesn't it?
Well, it goes through Y.
Oh, that's right. I'm doing it that way. That's it then, huh?
Yeah.
Yeah, I think so. Okay. Well, that was really easy, actually. So you know that then now I can go back to the other equation, right? So I can look here and I can say, okay, I probably want to take moments about Y now because I know I just eliminated a term. And so if I look at that, I know MB, I'm going to write it. Why am I writing it? Because if I misdetermine the other thing, now I've just added another mistake. And you know, I can just immediately put a little 0 there or something like this, right? And so what else is going to make moments about Y?
BX times the Y one.
And the
The force. So BX.
oh, I have an MCY too, don't I? Yeah. This is actually minus plus MCY. Then BX is going to be negative, right? Yeah, let's put that length in there. 1.5, right?
Yeah.
And then this other distance is 4. I'm trying to get through this, so I would usually try to be a little neater. All right, so minus 1.5 BY. No, yes, BX. And, oh gosh, all right, so about Y, so the only distance is Z, right? So it's going to be, I'm assuming it's plus. If it's not, we'll change it later. So I have 5.5, that's the Z distance. So about the Y-axis, I need the X part, 250 cos 60, and let's check the sign. So that's going to be, that's going to be in the positive X direction. Because 60 is less than 100, or less than 90 degrees.
Oh, yeah.
Right, so ignore how I drew it. Look at the. If it's only 60 degrees from the x-axis, it means it's going to have a positive component because cos 60 is a positive number, right? So if it's positive, that's going to make a positive moment about y, because it's like z cross x is positive y. Okay, this is hard at the time of the afternoon. All right, but that's not great because we don't know bx and we don't know. Yeah. Let's see here. We can get sum of forces in Z. We can also do sum of forces. No, we can't. Yeah, so I don't want to write out any more sum of forces on this one because like it's hopefully straightforward for you. And sum of moments about x, maybe let's just write that out. So sum of moments about x is going to be similar story. So we don't have a MCX. We do have a minus MBX. Then it's going to be plus 1.5 BY. And then it's going to be minus, I'm just taking your word for it, 5.5, right? Cos 40, 45 times 250, right? That's not directly accessible, but let's see if we can, if there's an obvious, MBY is 0. No, that's not what we want. We want MBX. But MBX we know. All right, so that was an easy one too. So MBX is 800. So I'm not going to solve that, but you can, right? So that gives you another thing. Right, so now you would have By, so probably sum of forces in Y now would give you Cy. We did all the moment equations here, sum of forces in X. Yeah, so now it's just a matter of writing out the additional one. So again, knock out as much as you can before you resort to matrix methods. And you could always go nuts and it would actually be kind of easy. And since it's homework, you could maybe, none of you have used Mathematica, have you? So Mathematica would make this kind of straightforward. You would literally just write out all 12 equations, and then you'd put them in what's called a list, and you say Mathematica solve these 12 equations, here's my 12 unknowns, and it would give you 12 values. Really nice. What's that? Yeah, but you don't have to set up a matrix. You just write it. I find it's easy. You're going to write out. So you have to draw free body diagrams, right? Write out all the equations, and then translate those equations into a matrix. A 12 by 12 matrix is no small thing. There's 144 things in there, right? A lot of them are 0.
I did an 8 by 9.
Yeah. So the smaller you can make this thing, the better. Yeah. I'm sure you can do it in smaller systems by finding more of these things first. Okay? All right, any other questions? So we've walked through a good chunk of these two kind of beefy problems. And just, for your well-being, mental well-being, we're not going to give you these sort of problems on the exam. We might ask you for aspects of these problems on the exam, but we can't get through that much. We also, frankly, couldn't grade it in any reasonable amount of time, right? Because there's just too many choices that you have. Okay, anything else? All right, then I guess we're done.